So Fischer projection is one of the toughest things that you're going to do visually. For a lot of people, it's something that takes practice and you've got to really focus on trying to see it. So what I want to do here is I want to introduce it with a little model kit. If you don't have a model kit, you don't need one. That's fine. If you do have a model kit, this is a great opportunity to use it. So I'll show you what I'm talking about in a second. But a Fischer projection basically is just a way to represent a chiral center in a nice 2D simple representation. And you're like, yeah, you say simple, but like, I know it's not going to be simple. So the goal is we are showing the chiral centers of a molecule, but in a simple 2D, two-dimensional, not 3D way. The way to think about this is imagine that we're looking at the molecule and we're kind of looking at this top-down view of the chiral center. So what do you mean by top-down? So first of all, in this molecule, where is a chiral center? Hopefully at this point, this is pretty comfortable to you and you're like, oh yeah, okay, that is the chiral center because I've got 4 different things attached, a bromine, an H, an OH, and then a methyl. Great. And if you're like, I did not recognize that, then you've got to practice chiral centers more a little bit. So the idea here is, imagine we are standing above this chiral center and we are looking, that's our little eyeball here, we're looking down at the chiral center. When we look down at the chiral center, imagine you're looking kind of like at the spine of the molecule and all the things are kind of splayed out. What we see is the Fischer projection. So let me show you on the model kit here. So what I have is I've got the black carbon here in the middle, right? We don't really see that because we're kind of covering it up. I've got the OH, that's my red atom. I've got the methyl, which is my purple atom here. And then up towards our face, that is the blue bromine. Think the blue bromine, right? And then the H green away from you. These colors don't mean anything. I'm just trying to give you nice, pretty colors so you can track what's going on. So here's the idea. This is our line angle. This is the way that we normally view a line angle. So we can't draw it like this though, so we draw it a little bit like that. So you can see the wedge over there to the side. So here's our zigzag of the line angle. So if I was looking down at that carbon, so we were standing up here, looking down, top-down view, here's what happens. If we have a top-down view, we turn it like this, and this top-down view, this is our Fischer projection. We are looking down the spine of your parent chain, and then those things are pointing off to the side that were substituents of the parent chain. So one more time, we're going from a line angle to a top-down view of the chiral center. That is what our Fischer projection is. So one more time, and if you're like, I get it, then move on. Because if you can visualize this, awesome. That's going to make your life so much easier. If you can't visualize this, you've got to practice it. I'll give you a couple ways as well. But we are going from a line angle, we're bringing the parent chain, which we'll talk about that in a second, up to the top of my projection, and that is what we're going to draw. So here's how we draw Fischer projections. We're going to practice this. The Fischer projection was that little crosshair. That's all it is. So here's our crosshair. We're looking top down at it. What does the center of the crosshair represent? A carbon, right? Chiral center. So that carbon in the middle is your chiral center. We don't draw it as a C. We just draw it as an intersection of lines like we're used to at this point. Then the vertical represents the parent chain. So in what we just did, I would say I brought the OH up to the top of my Fischer projection. So I'll bring the OH to the top. Then the rest of the parent chain would be the CH3. That's the purple atom, right? That's pointing down. So that is the bottom of my vertical chain, the bottom of my parent. Then this is the hard part. I would always start with drawing your parent chain in the vertical because then that kind of gives you a reference, gives you a backbone or a spine. Then the hard part is, which side does the bromine go to? Which side does the hydrogen go to? If we are bringing the left side of your line angle up to the top, what happened to the blue bromine? It goes to the left. So there you go. Then process of elimination, H must go to the right. If you can visualize that, if that makes sense to you, awesome. You're golden because that's going to be so easy for you. But if you can't visualize it, let me give you one more method that does not use a model kit, because if you don't have a model kit or you're not going to use a model kit on your exams, okay, fine. So here's what you do. Take your right fist. Do it with me. Take your right fist, put it on the paper. Your index finger here, imagine your fist, your hand itself, it is the chiral center. Your index finger represents this OH. So that's your parent chain. I want that parent chain to be, in the end, at the top of my Fischer, but we'll come back to that. So that is my OH pointing down to the left. Then your thumb points up towards your face. What is your thumb in this case? What is pointing up at your chiral center? That would be your bromine. Okay, when you rotate this, I'm bringing the OH up to the top of my Fischer. What happens? Bromine goes to the left. So there you go. That's the other way to do it. You're just taking your hand and just turning it. So you're always making this little kind of L shape, and you're just turning it like that. And there you go. That works every single time. As long as you're bringing the left side up to the top of your Fischer, whatever was up in the air is going to go to the left-hand side. And that works in reverse too. We can bring it back like this, and we can go back to the wedge. Now here's the thing. If you're like, wait a minute, but what if I do this and then I do that? Wouldn't it be on the right? Okay, don't do that. You're just making it harder for yourself, so don't be that person. But instead, all we're doing is turning it up to the top so that now you're looking from the spine, from the top-down view, and the thing that's on the wedge ends up on the left-hand side. Boom, that's it. That is your Fischer projection. It's going to get more difficult because we'll have multiple chiral centers, but for now, that is your Fischer projection. Now, let's go through some of the rules here. Here are the rules of the Fischer, and a lot of people try to argue these rules, and they're like, I want to do this. You can't. Rules are rules, right? So, the vertical chain in the Fischer represents the parent chain. And in a Fischer projection, the top and the bottom of the Fischer are actually oriented in a way, if you remember from here, that red and that purple atom, sure, they're vertical, but technically they're also pointing a little bit down away from you. They're pointing like down into the paper. So some people look at this Fischer projection and they like to draw it like this, where these things are on dashes. That is not the way that we draw a Fischer, but that is what it represents, yes. So those things are on the vertical chain, they're really kind of pointing down away from you like that. So those things pointing down, think like on dashes, that's the top and the bottom of the Fischer. On the horizontal, those branches, those represent substituents coming off of your parent chain. And again, what happens to those substituents? Sure, they're left and right, I agree with you, but if you'll notice, just based on kind of the geometry of this carbon, they're both pointing a little bit up towards our faces. So if you look from the side view, you can maybe tell a little bit better, but they're pointing up. The green and the blue atom are pointing up towards our faces a bit. So again, some people like to draw those on wedges because they're really up towards your faces on the horizontal. Again, we don't draw Fischer projections like this, but that is what it represents. The actual drawing of the Fischer is just lines, just crosshairs, just simple lines. So the horizontal would be substituents, and they're pointing up towards your face. One more time. Those are rules. Some people say, well, wait a minute, but I thought that H was on a dash. Yes, in the line angle, it was on a dash. In the Fischer, though, this is defined to be a certain way based on the geometry of kind of looking down the spine of the carbon. So if you're comparing molecules in a Fischer, and here's the thing, a Fischer projection, it's not fun to make. I agree with you. But once you make a Fischer projection, and we'll see some of these in the practice problems, making comparisons is actually really nice and really easy in a Fischer projection because it's a very simple view of a chiral center. So if you have Fischer projections and you're comparing a bunch of different Fischer projections, sure, you're allowed to rotate a Fischer. You can take the top and bring it down to the bottom and rotate it around, sure, but you cannot, and this is the important part, you cannot flip a Fischer projection over onto its back. Why not? Well, again, the definition of a Fischer is those things on the vertical are pointing on dashes. They're pointing away from you. If you try to flip this thing over onto its back, well, now those things are up pointing towards you. That is no longer a Fischer projection. So you are not allowed to flip it over on its back. It must always have that top-down dashed view for the vertical chain. Cool. That's the rules of the Fischer. Practice Fischers. It's not going to just come at you and be easy. If it is easy, that's awesome. You're in like the 1% of people studying orgo. But usually it's not going to be like that. Let me do a tougher one here. Multiple chiral centers. What if we have multiple chiral centers? It's the same process. The only difference is when you have multiple chiral centers, it is very useful to use what we call a tabletop projection. Some people call it like a flat back projection or a picnic table projection as a middle step, kind of like an intermediary step. So let's take this 3 chiral centers and turn it into eventually a Fischer projection. So let's start with the end goal. What is the end goal? The end goal is to represent all of my chiral centers on that kind of nice crosshair, simple Fischer projection. So the first thing I've got to do is figure out, well, where are my chiral centers? So take a moment, pause the video if you want, identify where are the chiral centers in this molecule. So hopefully you paused it. I don't know, maybe you didn't pause it, but hopefully you did, because you've got to practice this yourself. There should be 3 chiral centers that you identified. I've got the OH here, I've got a methyl, some other carbon chain, and then I've got the hydrogen. I'm going to draw my hydrogen that's on a wedge, so I know that it's there, because I don't want to forget anything. In a Fischer projection, you don't get to just ignore stuff. You got to draw all the things that are there. Similarly, down here, bromine's on a wedge, so that means there must be an H on a dash. At this carbon, if you're like, well, that's not a chiral center because it's just a methyl. Remember, methyls, sure, they can be unique. They can be different. Let them have their day. So I've got the methyl up on a wedge. That means I've got an H on a dash. And I've got these 2 very different carbon chains. So those are my 3 chiral centers. This is not a chiral center. It doesn't have 4 different groups because it's got a double bond. So we've got 3 chiral centers. So the goal is eventually we're going to turn this into a Fischer projection. So if you want to go ahead and draw your Fischer projection, the skeleton of it, to kind of give yourself some reference here, because there are 3 of those chiral centers, we should have 3 intersections of lines. I'm drawing it very carefully, so my awful handwriting is still legible somehow. Okay, the hard part for a lot of students is like, well, how do I know what goes to the top of the Fischer projection? Technically, there are some rules, and the rules are based on something called the degree of oxidation, and you're like, oh, that sounds terrible. Yeah, I agree. If you want to Google it, fine. Have a nice sleepy bedtime if you want to read about that. But the real reason that certain things go to the top is just based on some IUPAC naming rules. So things like carboxylic acids, aldehydes, ketones, alcohols, in that order, those things are higher priority groups. So those generally go to the top of my Fischer projections. So if you're ever in doubt, you've got to follow that ranking. Carboxylic acids, aldehydes, ketones, alcohols, and of course there's more. Again, you can Google it if you want to, but those are the high priority groups. So we're going to bring those up to the top of the Fischer projection. Before we do that though, I want to use our tabletop or flat back method. Here's the thing. There's another method I'll show you at the end, but this is generally best if you have multiple chiral centers, so you're not just guessing and checking, because that could take a lot of time. I've got 1, 2, 3 chiral centers. I'm going to draw a big old picnic table. So here's my picnic table. I've got a little edge of the picnic table here. Because I had 3 chiral centers, I'm going to have 3 dots of my tabletop or my flat back. When you're going from the line angle to your tabletop, don't do any changing of like what is the left and what is the right. Leave those as they are. So I've got 1, 2, 3 chiral centers. I'm going to leave it as 1, 2, 3 for my chiral centers. Okay, on the left-hand side, off of my first chiral center, what do I have pointing down? You have a CH3, right? So let me go ahead and draw that in so you can see it. CH3. I still have a CH3. So that's still the parent chain pointing down off of my tabletop, my big old picnic table. Then I've got the first chiral center, the second chiral center, the third chiral center. Then what? I've got COOH. So here I've got COOH. Start with your parent chain. That'll give you reference. So here's how we make the little tabletop. If your line angle is already pointing up, remember the goal of this is like we want a spine. We want to be able to look down the spine of what we have. So like if it's already pointing up, great, change nothing. So that means your OH is on a dash and your H is on a wedge. Perfect. If your line angle is pointing down though, what we have to do is imagine we're kind of flipping it up so that it's pointing up so we can look down the spine. So when you flip it up to point up, that means dashes and wedges flip. So your bromine becomes a dash and then your H becomes a wedge. And again, this tabletop, it's not a real molecule. It's just a projection, just a view to get us to the Fischer projection eventually. And then what about the third chiral center? It's already pointing up, change nothing. So I'm going to keep the H on a dash, and that means the methyl on a wedge. If you're like, wait a minute, Peter, but you flipped the left and the right. That actually doesn't matter. Doesn't matter, doesn't make a difference. What matters is what is on a wedge and what is on a dash. So that's all that we care about. Okay, that is the middle step. So it's like we're going from here to here, and then from here to here. So like I said earlier, how do I know what goes to the top of the Fischer projection? Things like carboxylic acids, those are higher priority groups. So in this case, I already did for the first problem if the left side goes to the top. Now I want to do a different one. So I wanted to give you practice if the right side goes up to the top. So that means this COOH is going to come up to the top of my Fischer projection. So COOH up here. Then I've got my first chiral center, my second chiral center, my third chiral center, and then the rest of the parent chain, which sometimes could be long, an ethyl, a propyl, a butyl. In this case, just a methyl, just a CH3. Once again, now we have the skeleton. Now we have the vertical chain of the parent. The hard part is, what happens to my dashes and my wedges? So earlier, remember, what we did was we said, well, if the left side goes to the top, we're going to use our right hand to represent that. Well, now we're doing the opposite. So use your left hand. What does your index finger represent here? Your index finger represents the COOH. What does your thumb represent? Your thumb represents the methyl, the thing that's just up there on a wedge. And if you want, and I'll just draw this in so you can see it, that is the methyl on the wedge. Okay, so one more time. The index finger is your COOH group, and your thumb is the methyl. So what we're doing now is we're saying, I'm going to bring this up to the top of my Fischer. What happens to that methyl? What happens to that wedge? It goes to the right-hand side. So one more time, we're going to bring that index finger, little wiggling index finger, up to the top of my Fischer projection. And what happens? The wedge, the methyl, goes to the right. So that means the methyl is on the right. Now, you can also memorize this. Of course, you can memorize it. And I'll show you how at the bottom here if you want to try to memorize it. But I'm recommending that you try to visualize it, because if you can visualize it, that's going to make this step a lot faster for you. All right, if the methyl's on the right, that tells you everything you need to know. That means the H must be on the left, and then you just follow the same steps. Again, what we're really doing is, imagine we've got our little eyeball here, and we are looking down the spine of my tabletop, and we're just creating the Fischer from that. So if the methyl here is on the right-hand side from the wedge, if you go to the next chiral center, same thing applies. That H on a wedge must be on the right-hand side. Go to the third one. That H, also on a wedge, also on the right-hand side. Then process of elimination, then you know where the bromine and where the OH are. So bromine would be on the left, and OH would be on the left as well. There you go. That is how we go from a 3, 4, 5 chiral center chain to a Fischer projection. Now, the visual thing, if you're like, I just don't see it. I don't see the visual thing. Okay, fine. Then you can memorize this, and memorizing works. I'm not going to say that memorizing doesn't work, of course, but this class is really difficult, and the more that you could try to understand and try to visualize, the less you have to store in your brain. It is going to make it nicer for you. But if at the end of the day you just can't see it, here's the rule. If the left side of your line angle drawing goes to the top of the Fischer projection, like the first one that we did, well, in that case, what happened to your wedges? The wedges go to the left of the Fischer. So you say if the left side goes to the top, then wedges go to the left side of your Fischer. And then again, by definition, the opposite must be true. The dashes would go to the right. Great. If the right side goes to the top of the Fischer, which is what we did in the second example, if the right side goes to the top, then what happened? All of those wedges ended up on the right side. So you can think of it like, oh, so the wedges kind of follow whichever side goes to the top. Yeah, that's exactly it. That's all that we're trying to do. So that is the way to visualize it. One more thing. Let me give you one more thing here because it's important, and I want you to have this tool. If all else fails, I said you could guess and check. What do I mean by guess and check? Well, remember, chiral centers have an R or an S configuration. So if I were to say, what is the RS configuration? What is the absolute configuration of that chiral center? You'd say, well, bromine is number 1. The OH is number 2. The methyl is number 3. So this would be a counterclockwise arrow. Remember, that's all based on atomic number, just literally the number on the table. So 1, 2, 3, counterclockwise. 4th is on a dash. Remember, dash is cash. So that means this is an S configuration. What that means is the Fischer projection that you build has to have an S configuration. So if you're paranoid or if you're just playing it safe, once you build a Fischer, check it. Check the RS configuration. But there's one little wrinkle here. The priorities are the same. So bromine, OH, methyl, okay, fine. So this would be oh, wait a minute, it's a clockwise arrow. Ooh, is that bad? Well, remember, the definition of a fissure is those things on the horizontal are up on wedges. So, sure, it's clockwise, but if your fourth priority is on a wedge, remember we have to flip it. So that's also an S configuration. So, yes, it matches, but just something to keep in mind that will trip you up. If your fourth priority is on the horizontal in a fissure, remember the horizontal by definition is up towards your face. That's up on a wedge. That means it's flipped. So the guess and check method is fine. It works. And if you're ever unsure about which one's on the left, which one's on the right, check the configuration and then you can check to make sure. The problem is that gets really ugly with like 3 and 4 and 5 chiral centers. You could have a lot of different possibilities there. So that's why that little flat back tabletop method is going to save you some time if you can visualize it. But that is the end goal. That's Fischer projections. It's tough. You got to practice it, but that's it for now. So we'll keep going.